Let's try to solve this question here. So you have two isotopes of a certain element having binding energies that differ by 5.03 MeV. So you have two isotopes of a certain element. So we are specifying that there's a particular element that we are going to study its two isotopes. So if you are specifying a certain element, a specific element means by they are going, because each element is defined by their specific proton number. So if you are talking about a specific element, that means by we are specifying the Z over here. So the Z is the same for both isotope. Okay, so there are two isotopes but of the same element. So because they have the same element, the Z should be the same. So each element is defined by their proton number or their atomic number. So if you say your Z is equals to 1, that's 1 proton, that's hydrogen. If you say Z is equal to 2, that's 2 protons, that's helium. If we talk about Z is equal to 3, 3 protons, that is lithium. So each element has their own proton number. So if they are specifying a certain element, that means by they are specifying the number of proton, they are specifying the value of Z over here. Okay, but you have two isotopes. So if there are two isotopes, isotopes means by they have different number of neutrons. So you have the same number of proton, but you have different number of neutron. That's the idea of isotope. So let's say hydrogen has a few isotopes. So you have deuterium, you have tritium. So you can have a proton with 0 neutron, that is also a hydrogen. You have 1 proton with 1 neutron, that is also a hydrogen. You have 1 proton and 2 neutron, that is also a hydrogen, because all of them have the same number of proton, which is 1, but they can differ in their number of neutrons. And these different kinds of combination, we call it as different isotopes of hydrogen. Okay, but here they didn't specify what type of element you have. They just say that you have a certain element, you have two isotopes, and the binding energy for these two isotopes, they differ by 5.03 MeV. So one of the isotope will have a larger binding energy, one of them will be a smaller binding energy, but they differ by 5.03 MeV. The isotope with a larger binding energy contains one more neutron than the other isotope. So maybe this is time for us to probably list out everything more clearly. So here we have isotope 1, and we have isotope 2 as well. So one of them should have a greater binding energy. Let's call isotope 1 to have a greater binding energy. So this one we call it to have a greater EB. Okay, whereas isotope 2 will be the other side of things, which is smaller EB. A smaller binding energy for isotope 2. So right now, because they say that the isotope with a larger binding energy means by isotope 1, contains one more neutron than the other isotope. So that means by if you compare isotope 1 and isotope 2, isotope 1 will have one more neutron compared to isotope 2. So if you want to represent it in terms of an equation, you can say that the number of neutron for isotope 1, it's n plus 1. Whereas the number of isotope for number of neutron for isotope 2 is just n. So comparing n2 and n1, you can see that n1 you need to add on another one, means that it has 1 neutron more compared to isotope 2. But if you talk about the number of proton, the number of proton for isotope 1 and the number of proton for isotope 2, they should be the same. So we are going to equate it to Z. Both of them should equate to Z. Okay. Then also we know that the binding energy differ by 5.03 MeV. So since isotope 1 has a greater binding energy, we can say that EB for 1, if you minus it with the smaller EB, which is EB for 2, you will get 5.03 MeV. That is what you get from the information from these two sentences over here. Now what does the question ask for? The question asks to find the difference in atomic mass between the two isotopes. So difference in atomic mass, maybe they will ask if you have mass atom 1, which should be the more massive one, because it has one more neutron, right? So mass atom 1 should be more massive. You minus it with the less massive atom, which is mass atom 2. What would be the value over here? Okay, so to solve it, probably I'll start with this equation over here, because this binding energy here can be related to the mass of atom. We just need to use the correct equation. We know that binding energy is equals to mass defect times c squared, and mass defect you can represent in terms of mass of nucleus or mass of atom. In this case, we are going to represent it in mass of atom because that's what we want to find the difference with. So there are two equations that has mass of atom in it. We are not going to use the one with hydrogen because they don't give us information about the mass of hydrogen. Probably we stick to the one that has protons, neutrons, and electrons in it. Okay, please refer to the explanation video if you're not sure what three equations I'm talking about. But basically, we are going to pick the one that has atomic mass in it, and we are going to take the one that use the atomic mass, remove the electron that is orbiting around the nucleus to then from there we get the mass of nucleus. That's the approach that we are going to go. Okay, so from here you can say that EB1 minus EB2 will be equals to 5.03 MeV. Okay, so if you expand EB1 and EB2, we know that EB1 is delta M, the mass defect for isotope 1 multiplied by c squared, whereas EB2 will be mass defect of isotope 2 multiplied by c squared, will be equals to 5.03. Okay, we can factorize out the c square one side, factorize out the c square, then we can expand what we know for delta m. Okay, I think this delta m here will take a lot of space. So delta m1, we're going to expand it first. So delta m1, we can expand it to be the Z mass of proton, but this one is isotope 1, so Z1 mass of proton plus N1 mass of neutron. So this is the mass of separated constituents right now. We're going to minus with the mass of nucleus, but we are going to obtain it from the mass of atom. So we're going to take mass of atom 1 minus the number and the mass of electron, but this one is Z1 minus mass of electron. So this bracket here will allow us to determine the mass of nucleus because we will remove the mass of electron from the mass of atom. Okay, so everything here will give us the mass defect for isotope 1. Okay, so we are going to square bracket it. So this is mass of isotope 1 minus, now we are going to find the mass defect for isotope 2. So it's a similar equation, just change everything to be Z2 MP plus N2 Mn minus mass of atom 2 minus Z2 multiplied by the mass of electron. So everything here will be the mass defect for isotope 2. Okay, so maybe I should change it to a larger bracket over here to multiply by c squared. So this whole thing here multiplied by c squared will give us 5.03. Okay, so now what I'm going to do is I'm going to expand the brackets over here. There's plenty of brackets, but I'm going to expand it so that we can see what can be crossed out. So you have Z1, I'm going to equate it to Z, should we substitute with Z? So this will be ZMP plus N1, I'm going to substitute with N plus 1. So if I expand it, this will be N Mn plus Mn. Okay, I substitute in N plus 1 and I expand it immediately. Okay, so this will be N plus 1 being expanded. Okay, so minus mass of atom 1. Okay, then after that minus negative, this will be positive, so plus ZME. Okay, I'm going to change Z1 to be represented by Z. So minus Z2, so Z2 again represented by Z and P minus positive, so this will be minus, and 2 is going to be substituted with N, so this is NMN. Then you're going to have minus minus, so this is plus mass of atom 2 plus mass of atom 2. Then you have your negative, so this will be positive, and then positive multiplied by negative, you get negative. Negative ZME. Z2 replaced by Z. So everything here multiplied by c squared will give us 5.03. Okay, just from comparing the terms over here, you can see that something can cross out. There's a positive ZMP, there's a negative ZMP, there's a positive NMN, there's a negative NMN, there's a positive ZME, there's a negative ZME. Okay, so from these things itself, I think we can see that we can simplify the whole equation much more. So now the equation will be something like this. You have Mn minus, but I'm going to factorize out the minus, so this will be mass of atom 1 minus mass of atom 2. Okay, so this whole thing here multiplied by c square equals to 5.03. You might need to take some time to digest this thing because I'm factorizing out the negative sign over here. So this one, if you multiply in, you get negative m atom 1. Negative, negative, you get positive m atom 2. So this is the equation after simplification. And mass atom 1 minus mass atom 2 is basically what we are finding over here. So we should shift everything to the right hand side. But before we shift, we have to be very careful. This 5.03 here is in the unit of MeV. Okay, so maybe what you should do is you should convert the mass over here to be in the unit of MeV over c square, so that it can cross out with the c square over here to get answer MeV. Okay, so because this mass over here is in the unit of U, we need to change it to MeV over c square. So I'm going to put it somewhere a bit to the left. Mass atom 1 minus mass atom 2. This whole thing here, I'm going to multiply, I'm going to eliminate the U, introduce MeV over c square, just to switch it to the correct unit. So once I switch it with the correct unit, I can proceed to multiply the whole thing by c square in order to get an MeV answer. Okay, so this c square and this c here can cancel out. Then if we shift things to the other side, you get that mass atom 1 minus mass atom 2. We can obtain this by taking 5.03. Okay, we divide by the 931.5 first. Once we divide by the 931.5, we are left with mass of neutron minus this thing. Shift the m atom 1 minus m atom 2 to the right hand side and bring this thing to the left. Then you get this one to be negative. Then you have a positive mass of neutron. Okay, so if you proceed to do a substitution, okay, I don't have that space, so I'm going to substitute mass of neutron here immediately. So mass of neutron here is 1.008665, just as being indicated over here. So calculate everything, I'll get my answer to be equals to 1.003265 U. Okay, so this will allow us to determine the difference in the atomic mass between the two isotopes. Okay, so this is a slightly different way of asking questions related to mass defect and binding energy. Again, they will tell you the relationship between the number of protons for the two isotopes, the number of neutrons for the two isotopes, and their binding energy. So if you are able to expand the binding energy properly, carefully, then you see that there are many terms that can cross out, allowing you to determine the difference in mass, difference in the atomic mass. Okay, but what I think students might have trouble with is to convert the unit over here, because everything is in MeV. So definitely for your mass defect over here, you have to change it to MeV over c square first using this conversion factor. Only can cross out the c square, only you are able to bring everything to the right hand side with no problem to the unit. Okay, and the answer for this question here should be in the answer of atomic mass unit. Of course, if you want to switch it to kg, that's not a problem. But if you are using this 931.5, remember the mass defect should be in the unit of atomic mass unit.